Good morning, everyone. It's the second day of the summit. How's everybody doing? Thank you so much for joining me today. My name is Xinran Weibo, and I'm part of the personalization data engineering team at Netflix. Here, right next to me, is also my colleague, Syndrome, and he's part of the real-time data infrastructure team. We're very excited to be here and share with you how we backfill data pipelines in Kappa architecture. Here's the agenda for our presentation today. First of all, to set up some context, I'll share with you about our event streaming use case at Netflix, why we need to backfill streaming pipelines, along with all the existing approaches and their pros and cons. Then Syndrome will take over the stage and walk you through our solution for backfilling in Kappa architecture with Data Lake. The most exciting part of the whole presentation, in my opinion, is how we tackle the event ordering challenges. So in case you fall asleep any part, stay awake for that part. And at the end, I'll come back again and show you how we adopted Kappa Backfill for our own streaming pipeline, and also some of the lessons we learned from backfilling in production. Sounds good? Everybody ready? Buckle up, let's get started. So before I get into all the technical details, show me your hand if you watch Netflix. Great, great, I see so many Netflix fans here, but also some hands down. You guys are missing out big. Anyway, another question, have you ever seen others' Netflix homepage and just realized it's so different from yours? Some hands, notice that? Great, great. You know, I remember I visited my in-laws' family during Christmas, and they were playing Netflix on their living room TV. And I just noticed how different it looks like from mine. And it almost looks like as if Netflix has a secret catalog for them, but not for me. And that difference makes sense because they have so different tastes in TV shows and movies compared to mine. So Netflix is able to deliver unique user experience to every member thanks to personalization. And behind those personalization algorithms are our event streaming data system that's powering it. I'm part of the personalization data engineering team, and my team built various data systems that enable data analytics, machine learning trainings. And one of such systems I want to show you is this real-time merge impression Flink application. The main purpose of this application is to calculate take rate. Take rate is basically the number of times a show is played divided by the number of times a show is presented to the user. And take rate has many use cases, machine learning, algorithm training, A/B experimentation analysis, and more. So to calculate take rate, the RMI app joins real-time impression events with playback events to attribute plays to impression. And given Netflix data size, it is actually one of the largest stateful Flink applications we have at Netflix. Real-time data insights are always so exciting. It opens us the door for so many new opportunities. However, event streaming operations, it's not so exciting. Just like any other software applications, streaming jobs can fail too due to many different reasons. For example, you might have same source failure that your application cannot read or write anything. You might have dependent service failure that your app cannot enrich the data, therefore producing incorrect output. Last but not least, upstream data change. Show me your hand if your job ever failed because upstream data changed. Yes, yes, many hands here. That's a big pain point in my life. I mean, in data engineering too. And just like most problem here on this meme, after job fails, we recover the job. You know, my job isn't done yet. Because our streaming pipeline serves such important data input to our algorithm, experimentation analysis, and even product experience, we have to backfill the data to mitigate downstream impact. There are some of the possible backfill needs you might find. For example, correcting incorrect data that produced by your app, backfilling missing data from earlier history, or even use the historical data to bootstrap state for your app so that it can continue to consume the live data. So that's amazing. We have to backfill all the time. But the bigger question is, how should we backfill? The easiest way to backfill a streaming job is by replaying our streaming job and reprocess the source event from the problematic period. Sounds easy, right? You just redeploy your job, set the Kafka offset, and wait for it to catch up. However, there's a lot of problems with this approach. First of all, when failures happen, troubleshooting the root cause can take you hours or days, and your source data can expire. And when that happens, you are facing a data loss, and that is no good. And you might ask me, well, why don't we just increase in retention so it never expires? The truth is, increasing message queue retention is very expensive for 2 reasons. First of all, events in message queue are often stored in row-based formats, such as Avro, which doesn't have as good as compression rate as columnar formats such as Parquet. And secondly, message queue require low latency data storage like SSD, which is a lot more costly than object storage like S3. So at Netflix, let's say if we want to store 30 days of all data from Kafka, that would be 33 million a year. That's very expensive, and we're not doing that. So if storing data in Kafka is so expensive, can we store those events somewhere else and backfill from there? At Netflix, we use the Keystone platform, which provides a really convenient routing service for us that make Kafka event also available in other storage systems, such as a data lake. So of many storage system options there, why data lake? For those of you who's not familiar with this concept, data lake is a centralized data storage that can store a large amount of data in its native format, usually in an object storage like S3. And some of the frameworks supporting data lake include Delta Lake by Databricks and Apache Iceberg. And for Netflix specifically, we use Iceberg. So come back to the question, why data lake? Because it offers many benefits. First of all, it's cost effective because its underlying data are stored in a highly compressed format such as Parquet, and it also have other many great features. For example, file pruning, which makes read performance really great. Schema evolution, like I said, data changes all the time. And last but not least is engine agnostic. It's really important for us to allow different data processing systems to read and write from the data lake. Here's just a quick example of how a Kafka event looked like when it was stored in an Iceberg table. As you can see, some of the high-level columns, like account ID, show ID, is translated into top-level fields in the Iceberg table, making it really easy for batch system to query them later. So we have the Kafka event also available in a data lake. Can we backfill from there? The answer is, of course, yes. That leads to our second option, the Lambda architecture. This approach is basically about building and maintaining a separate batch application that is equivalent to your stream application, but instead, it reads from Iceberg table. One big advantage of this approach is that Spark or other batch processing engines, they often offer really high throughput, so you can backfill historical data very quickly. However, there's always some problems. For your engineers to initially develop such application, it can take them days or weeks to write the code, and not even mention all the data validation work you need to do to make sure the backfill job produces the same output as your production job. And that's not over yet. As long as your streaming job is still in production, you have to keep the batch job up to date and up and running. Another option I also want to discuss here that might not apply to many of us is by using a unified batch and streaming framework. Frameworks such as Apache Flink, Apache Beam, they allow you to run your application both in batch mode and streaming mode. It almost sounds too good to be true, right? And in fact, in reality, it does come with many limitations. Here at Netflix, we use Flink. But we found out that to be able to let our stream application to run in batch mode, it still requires significant code changes. We don't use Apache Beam at Netflix. However, from its documentation, it seems like it only has partial support for some key streaming features like state, timer, and watermark. So that might not work for some specific use cases. I just walk you through 3 of the existing approach for backfilling. Let's just take a look at them side by side again. First, and the easiest backfilling option is by replaying your streaming job. It's easy. You just use the same application both for production and also for backfilling. But the main problem here is increasing message queue retention is very expensive. The second option in the spirit of Lambda architecture is by building a separate batch app equivalent to your streaming app, and you run the batch app for backfilling. The problem with this approach is that your engineers will have to maintain 2 applications in parallel, and that is a lot of work. The third approach is by using a unified batch and streaming framework that offers both batch and streaming mode. However, in reality, it might still require a lot of code changes. So as you can see, all of the existing options here are not so ideal, right? That make us think, can we possibly combine the best things from all 3 worlds and come up with a solution where everybody is happy? And that is backfilling in Kappa architecture. Syndrome will take over from here and tell you everything you need to know.
Thank you so much, Jinjan. That was actually great. I don't know how I'm going to follow up after that. Let's see. I'm going to try my best. So based on the previous pros and cons of the previous approaches that we saw, we arrived at the following goals for the project. Firstly, we want to provide a generic solution for backfilling streaming applications without tying to the business logic. This makes it easy to adopt it across a wide variety of streaming applications. Secondly, it should require very few code changes to add backfill support to your streaming application. This is very important because we don't want developers to spend hours or days building backfill support in their streaming application. Finally, it has to scale horizontally, as we want the developers to wrap up their backfill as quickly as possible so that they can move on to the live traffic. So the design of backfilling streaming data applications using data lakes is actually fairly straightforward. There's not too much details to it, but anyways, let's go over it. At a high level, instead of using a live source, such as Kafka, that's more optimized for latency, we will use the data lake that is more optimized for throughput during backfilling. What does this mean semantically? Semantically, what this means is that when the application needs to process live data, or in other words, the application is operating in near real time, it has to read data from Kafka that's more optimized for low latency. When the application needs to process historical data, it reads it from the data lake, which offers a very high throughput, and thus allows one to complete the backfill as quickly as possible. So before we dive deep into how we are going to leverage the data that's stored in the data lake for backfilling, let's first look at how the data gets ingested into the data lake. As events arrive in the streaming messaging system, they are batched into different partitions, for example, date, time, hour, or even batch ID, and then stored into very compressed formats such as Parquet. The reason we want to batch them instead of storing them individually should be obvious. This way, we get the benefits of efficient compression data format such as Parquet or Arc. Another reason is that we don't want to store all of these files individually is because we'll end up producing a lot of small files, and that would make it really inefficient at the time of reading. So the question is, we have all this data that's stored in the data lake. Now, how do we leverage it at the time of backfilling in your stream processing application? So the layman approach is to just read events from the files that are filtered based on the backfill duration. So let's assume that you have to read these 3 data files that are stored in your data lake for backfilling. You assign these files to the readers in your stream processing engine of choice, and the readers can then emit events by reading these files. Fairly simple, right? Now, there are some great properties about this approach. One is that it scales horizontally, and so you can throw more resources onto the problem and get the backfill done as quickly as possible. Secondly, it's very simple, so operating this in production is going to be fairly simple. But then there is a big significant disadvantage of this approach, which is that if you take this source and replace your live Kafka source or another source with this, then it may lead to incorrect results. So let's try to understand why that is the case. So let's consider this simple application. These type of applications are pretty common in production deployments. So what this application is doing is just sessionizing the playback source at Netflix and converting them to user sessions. So in this case, the user has watched all these movies. The application just sessionizes them. So this is a fairly simple application, and it's pretty common in production deployments. Now, if you were to replace or change the order in which the events arrived to this stream processing application, what you realize is that you get completely different results. The reason is because the application has made certain assumptions around the ordering of events. So if you were to break these ordering guarantees, then the application is going to produce incorrect results. So even though the backfill will work, it just will produce incorrect results, and the developers are not going to be happy about it. Now you think about this and you realize, okay, I know how to fix this problem. I'm just going to order the files based on the ingestion timestamp and then assign them to the readers in the exact same order. So what this means is that you're going to first assign data that arrived in the first hour, first batch. Once the reader is done with that, then you're going to assign the data that arrived in the same hour, but the next batch, and then the next hour, and so on. Okay, so this approach should provide similar ordering guarantees as the streaming source from which your application was originally reading from. So it should not produce any incorrect results. But then you realize this approach does not scale horizontally. So even if you throw more resources onto the backfill, it's not going to complete quickly because you're bottlenecked by the amount of parallelism you can get when you're reading all these files. So one thing you realize is that when you look deeply into all stream processing applications, they don't rely upon the strong ordering guarantees that messaging systems such as Kafka provide. And in order to understand this, let's go over the same example that we saw before. So if you look deeply into the sessionization application that we had considered earlier, you realize that sessions are generated based on the event timestamps, or the timestamp of the events. And because the events can arrive late, the application can typically tolerate lateness in these events. So the question is, can we use this lateness that is tolerated by the app so that in order to quickly backfill the data from the data lake? So let's try to understand this with an example. Let us say we have the same exact 5 files that we need to backfill. So here, the numbers in the boxes represent the timestamps of the events that are contained in the file. And we have the same readers as before. Let's assume that the application can tolerate a lateness of up to 10 minutes. We are also introducing a new state as part of the source called the ingestion watermark. The ingestion watermark represents the timestamp up to which the data has been fully processed from your data lake. So initially, it's set to 0, implying that you've read data up to 0th minute. Now, because the application can tolerate a lateness of up to 10 minutes, files in the time window 0 to 5, as well as files in the time window 5 to 10 can be read in parallel, as reading them will not violate the lateness constraint. However, files containing data between 10 and 15 minutes cannot be read because reading that will violate the lateness constraint. So you can see files 0 to 5 as well as 5 to 10 are essentially read at the same time. Once they are done and the reader says, hey, I've read all these events, then the ingestion watermark is updated to 5, implying that all data up to the 5th minute has been processed by your data lake. Now, since the application can tolerate a lateness of up to 10 minutes, files in the time windows 5 to 10, as well as files in the time window 10 to 15 can now be assigned in parallel. Now, this approach it solves the throughput problem that we saw in the previous approach. And typically, stream processing applications can tolerate up to a lateness of few hours, so we are not limited by the throughput that we saw before. It also provides the same ordering guarantees that your application can work with, so it should produce the same results as before. So this is great. So there is still one caveat. The one caveat is that the ordering guarantees provided by messaging systems such as Kafka are actually very different. For example, Kafka provides strict ordering within a partition, but most analytical use cases within Netflix do not make use of such ordering guarantees. Instead, they use event-time semantics and can typically tolerate lateness in their events. So we don't have any use cases that need such strong ordering guarantees. Now, there is still one interesting challenge that we have not talked about, which is that typically stream processing applications can read from multiple sources, and they generally read from multiple sources because they end up joining them or enriching them using the other source, for example. So in the case of backfill, these applications will now need to read from multiple data lake tables, which basically are backing up the original sources. However, the problem is that if one of the sources is significantly larger than the other, then it's going to lead to a watermarks queue. And if you have a watermarks queue, that is going to result in state size explosion, large checkpoint times, and so on. So these are a wide variety of problems you'll deal with if one of your sources is significantly larger than the other. This is also problematic. So the question is, how do we deal with that? So the idea here is very simple. Each of the, like we mentioned earlier, each of the sources has the state called ingestion watermark that tracks how up to what data has been already processed. So in this case, all the sources are set to 0 because they've all processed like 20 minutes data up to 0th minute. We're also introducing a new state called the global watermark. So you can think of the global watermark as representing the application's watermark, application's ingestion watermark that captures the whole of the application. Now, as you update watermarks for your individual sources, make sure you also communicate that to the global watermark. So in this case, source 1 and source 2 have watermarks updated to 5. You can now let the global watermark know that sources 1 and 2 have made progress. Now, you can see that source 3 is still lagging behind. So as a result, the global watermark is still only set to 5, meaning that the application's watermark is only 5. So the way we are going to use the global watermark is by making the source use the global watermark for the lateness constraints rather than using the individual sources watermark. So what this means is that source 1, even though its watermark is set to 5, or source 3, even though its watermark is set to 10, it is bound by the global watermark, which is set to 5. So you can only read up to, and let's say the application can tolerate a lateness of 10 minutes, it can only read up to the 15th minute. So this is how we make sure that all the sources are aligned with each other when we backfill. So to summarize, we saw a Strawman 1 approach, which is to just read files and assign them in any order. We realized that that is going to result in incorrect results. The Strawman 2 approach was to order the files based on the ingestion timestamp, but then we realized that this is going to result in a throughput problem. So our solution is to essentially read the files while still maintaining the ordering guarantees by making use of the lateness constraint that we saw. We also have this concept of a watermark tracker and a global watermark tracker that allows us to align the sources when we need to backfill. I'm going to now pass it again to Jintan to see how we are going to use this new source that we've generated based on the data lake to see how we can backfill using that in our stream processing application.
Thank you, Syndrome. That was a great overview. For the next part, I'll show you how we adopted Kappa Backfill in our own data pipeline, as well as lessons we learned from backfilling in production. First of all, let me show you how we set up the RMI application to enable Kappa Backfill. First of all, we have the real-time impression and playback events available in Kafka topic. And our RMI production stack reading from those real-time events and write to an output. Thanks to our Keystone platform, those real-time events are also available for querying in an Iceberg table. So we set up the backfill stack, which uses exactly the same code as our production stack, but instead it reads from Iceberg tables instead. So one of the main benefits of Kappa Backfill is that it requires minimal code changes to add support. And I want to show you some sample code to see how easy it is. So here is some Flink application code in Java. Don't worry if you don't understand this Flink syntax. Here we declare the live sources and sync. And to enable Kappa Backfill from an Iceberg source, you just need one line of code to add Iceberg source to your application. One thing I want to point out here is that the in-memory representation of this impression event is exactly the same between Iceberg source and live source. And thanks to that, you don't have to make any change to your processing logic at all. In addition, just a couple more lines to change in your app configuration file, and then you're good to go. So we backfilled RMI so many times in production, and we not only see high throughput, but also consistent data quality. We were able to backfill 24 hours of data well within 5 hours, and we also found the backfill output matches more than 99% with the production output, which is pretty good for us. So what are the lessons we learned from actually backfilling in production? First of all, the backfilling windows and configuration would heavily depend on your application logic, especially if you have a stateful job. So you would want to do some timestamp calculation, making sure that you process enough data to build up in sufficient state. And in addition, backfilling job will need additional tuning. The reason for that is because during backfilling, most likely the data would flow through your system at much higher volume per second. And you may want to allocate more memory or disk resources so you can achieve higher throughput for your backfilling job, therefore backfilling even faster. At the end, let's just take a look at all the benefits that Kappa Backfill has to offer. First of all, you can use exactly the same streaming application, both for production and for backfilling. And it's so easy to set up, only take a few lines of code to add support. And also, Kappa Backfill offers such high throughput that you can backfill historical job very quickly. Last but not least, it's cost effective. Previously, returning 30 days of Kafka data would cost about $93 million a year for Netflix, but now it only costs $2 million a year in Iceberg. That's all we want to cover for today's presentation. Thank you so much for joining us today, and I hope you enjoyed the presentation. And now I'll open up the floor for questions.
Is it okay? Quick question. In one of the slides, in the second last slide, you mentioned that the output matches 99.9%. Why not 100%? Why is this deviation?
So you're asking why there's still something missing?
Yeah, and whether or not it is acceptable, because if it is weblog, people could accept it. It's okay. If it's financial transaction, you wouldn't accept it, right?
Yeah, so that's a really great question. So this data quality kind of criteria you would accept, it kind of depends on your application logic. Because for my application specifically, we would kind of merge, in a way, the duplicate application, the impression events based on a set of keys. And then we set a timestamp for it, depending on the first event received. And and as Sandra mentioned, we can set kind of misalignment configuration for backfilling job so that it's like a maximum amount of time between the event timestamp of events that are flowing through the system. So the orders of event flowing through backfill job is a little bit different from the production job. So some of the events might end up getting a slightly different timestamp compared to others, or getting allocated to different event hours. But that small percentage really is really small, and we don't care that much. And that is where that data quality percentage difference we're seeing.
Can I add one more point?
Yeah.
Can I add one more point to that? Is it audible?
Yeah, I have a question. First thing, if you can maybe elaborate on, so the global state, the global watermark, where exactly do you save it? And also what happens, since you said that it's possible to run two applications, right, both the backfill and the real-time one at the same, to run the same jobs at the same application. So what happens if your state gets corrupt and you need to clear it? How do you make sure that your data gets ingested, gets processed only exactly once?
Yeah, that's a great question actually. So the first part was, where is the global watermark stored?
Yeah, where do you store it?
Yeah, so the global watermark is also part of the checkpoint state. So as part of the source operator, we also keep track of the global watermark and also checkpoint that. So that's how it's stored. And the second question was, what happens if it gets corrupt?
If the state gets corrupt, how do you make sure it's exactly once?
Yeah. So typically we don't offer exactly one semantics within Netflix. We generally offer at least one semantics. So if the state gets corrupt, you can always go back to the previous checkpoint and start replaying your job from that point onwards. So that's typically how we deal with it. Let's say your sink doesn't offer transactional support. Like for example, Iceberg offers transactional support. So even though we only guarantee at least one semantics, because of Iceberg we can guarantee exactly one semantics. But let's say you use Kafka as your downstream sink. In that case, we don't offer exactly one semantic. So the application will end up rewriting, or will end up producing a lot of duplicate events in the downstream sink. Did that answer your question?
Yes, thank you.
Can I add one more point about that 99.9% of correctness? So the one more thing that we need to know about is the backfill can actually produce more correct results than the live data. because of how Flink watermarks work and how you use the latest constraint, etc. So typically, even though there is a mismatch, it could be the case that the backfill actually is more accurate than the live results. Is that correct?
Yeah.
How do you take care of the late arriving dimensions with the real-time pipelines in your backfills? Because there are certain dimensions which would be missing, and the decoration.
Okay, please hold the mic to.
The decoration may be, late. So how do you actually make sure that all the late arriving dimensions are taken care of, whether they are in backfill or in the real-time pipeline?
So the lateness is actually handled by the stream processing application. So the stream processing application has this concept of watermarks. For example, let's say you get an
You're talking about the actual data which is coming in the fact, as a stream, right? Mm-hmm. But the thing is, the stream needs to be decorated too, because there are certain dimensions, like a video ID would be there, but what the video ID is, the name of the video or the name of the content. How do you actually take care of in this particular pipeline, or do you do it afterwards?
Oh, are you talking about kind of enriched video?
Enrichment, yes.
Oh, okay, yeah. So yeah, as part of this application, we would call some API service internally at Netflix to enrich the ID with more metadata information we need for analytical use cases. Yes.
I have a question. In the diagram that you guys showed, the output of this job was ending up in a Kafka topic and then going to Iceberg. And when the backfill is happening, is that still happening? And if so, if someone else is consuming the topic, what others need to do? Does that need any coordination of streaming jobs so that the backfill doesn't affect the rest of the pipelines?
Yeah, I think that's a really good question. I think that is a common challenge of backfilling, regardless of what approach you use, because when you backfill data, there's always going to be duplicate data, right? So we actually don't handle that duplicate specifically in our sync, but we kind of just defer that to downstream to handle it. If it's a real-time use cases, then they can set up some state, doing some duplication based on certain type of key, or if there's a batch-based duplication, then it can be handled by like a Spark job by doing some group by taking the latest data event.
Less about duplication, but about the amount of data that is going through. Because now there's a backfill, lots of data is going to arrive at the topic, and it's not going to be a streaming one, it's going to be a days ago's data. So the services that are consuming that will have a hard time.
Yeah, so the way you typically deal with that is you generally produce the output of the backfill to a separate Kafka topic, for example, and then merge let's say that ends up on an Iceberg table. So you merge these tables in the end. So that's how you typically deal with it. So you don't have to pollute or cause a lot of load on the live output itself. Did that answer your question?
Yes.
Yeah.
So are all of these backfill jobs triggered manually based on an ad hoc basis, or you have some orchestration layers that based on some status of signal trigger automatically?
Yeah, eventually we want to get to that. We want to do something called a magic source that can automatically switch back and forth between data lake and the live source, depending on where you need the data from. So that's something we want to automate eventually, but that's not where we are at today. It's pretty ad hoc in that the user says, hey, I want to backfill between 10 hours and 24 hours. From this source, and then that's how it is typically operated within Netflix.
Okay. Thank you, Shenran and Sundaram. If anyone still has any questions, feel free to talk to them after class.
Thank you.
Thank you.